what are finite state machines, finite state automaton? Finite tells you that the number of states in the machine is finite. It could be 2, it could be 10, it could be 100. And what are states? States, somehow they remember some computing information. So they remember some information about the computing that has taken place so far. And with this, we design machines meeting some specific application or a requirement. It may not remember all of them, it can remember few. Through examples, we will see what is that it can remember, what is that it cannot remember. In fact, that itself tells you that the limit of this machine is precisely this. We come across finite state machines in many applications. The simplest being, for example, look at any electrical or mechanical switch. You have two states, on and off. And initially, a machine or an equipment is an off state. You supply sufficient mechanical energy or electrical energy. You supply some energy, it could be electrical energy or mechanical energy. The machine starts operating, or so and so device starts moving, or some change you get to see. And when we pull back the energy, it comes back to off state. Okay, you see that drop in energy, or it is becoming zero at some point. And when it is an on state, you continue to supply, it stays in the same state. You continue to supply more energy, it continues to stay in the same state. So here is an example of a finite state machine which has got two states, and you get to see that when you move from this to this, and something has actually triggered you, meaning you have supplied some energy and which actually triggered you to move from one state to another state. So in particular, this one, supplying energy or pulling back, this is formally we say it is an input. This is also an input. And it is this input that changes the operation of the machine from this state to this state. And this state tells you that I received some energy due to which I am here. So that kind of information is what you can convey when you are at a particular state. Okay? But this may not tell you how much energy I have received to move from this state to this state. And you keep supplying energy, how much I need to supply to stay here, all that this description may not tell you. Maybe we need a different description to talk about this. Consider this example, which we often see in the context of scheduling. There are many tasks waiting for CPU. So these are all the tasks, and they are at the waiting queue. Okay. Or initially, when a task is placed for execution, it comes over here. And after some time, you schedule the task, then it goes to something called execution or running state. Now, while it is executing, the task or the underlying processor identifies that it requires some input from external source or some input output device. What happens? It actually moves this, or let me call this one as say suspend. From the current execution, it's being suspended and moved to this. Then it is being serviced here for a while. Then once it is done, it is placed back onto this. And once the service is done, it is placed back, which means you see that it resumes the operation. And once the execution part is done, then it goes to the result or output state. Okay. So now each state, this is an example of a finite state machine where when this action is triggered, that schedule, then it comes to this state. Then when you trigger this action suspend, then the task that is in execution or running moves to external source and it asks for input from some input output device, and once that is passed, it comes back, it resumes and it goes to the next state, which is called result or output state. So now you see that this finite state machine, each state is trying to remember something. When I am here, I know the process in execution is in need of some input from an external source. And when it is here, I know process is actually running. When it comes here, we know the process is done with its task and it is waiting for display or output. Now, on the similar line, we can model many computational problems using finite state machine. So, what is that you can model and what is that you cannot? How do you formally describe? All that we shall see next. Here is our next example that talks about 2-bit addition. In some sense, it is a finite state machine with output. Shortly, we'll see what you mean by with output. So, I've got two states. So, one I call it as no carry. Another state is called carry. Now, it is a 2-bit addition. So, you may add 0 and 0 or 0, 1 or 1, 0, 1, 1. Now, if you add 0 and 0, sum is 0, there is no carry. For this, sum is 1, no carry. So, for this also, sum is 1, no carry. For this, sum is 0 and there is a carry, and carry is 1. So, how are we going to describe this? So, initially, we will be at this one. So, this arrow says it is an initial state, or it is the initial state. Now, when you are here, it receives the input 0 and 0. So, let me call the first bit and the second bit. So, when I receive 0 and 0, what is the sum? Let me write the sum here. So, this is what I call it as output. It is a finite state machine wherein you describe the input as well as the output. So far, whatever we have seen in the context of switch or process scheduling, we were only talking about the input and changes from one state to another state. But over here we explicitly mention the output as well. For this input, what is the output? So not just the change of state, in addition to that, we also explicitly output something called sum for this example. Now, if the input is 0, 1, then sum is 1, there is no carry, so I continue to stay in the same state. Or the input is 1, 0, then you see that sum is 1 and there is no carry, so I continue to stay here. But when the input is 1, 1, now what do you get? You get to see that the sum is 0 and you go to this state. Okay, so this is a simple description where you get to see you move from this state to this state, and so this is precisely what happens. Now you can do some more description. Now I am in carry state. I get two inputs, say 0, 0, and you have a carry. Now what happens? For example, now I am in this state, say, and I receive this input, and you know that you already have a carry, so which means addition is something like this. So it is actually 0, 0, 1. So you get to see that sum is 1 and there is no carry. So at this point in time, you see that when you receive the input 0, 0, and you already have a carry, and with that sum is 1 and there is no carry from this. Now like this you can describe other cases. Suppose my input is 0, 1 and you already have a carry, which means what happens when you add this, sum is 0 and carry is 1. So when the input is 0, 1, you get to see that sum is 0, there is a carry, so I continue to stay here. Now on the similar line, when the input is 1, 0, sum will be 0, there will be a carry. Now there is a carry, with this you receive 1, 1, then you see that sum is 1 and carry is also 1. Correct? Which means there is a carry. When you receive 1, 1, sum is 1 and there is a carry. So like this it continues. So here is an example of a finite state machine which describes both the input part as well as the output part, and the states remember information. This says when I am here and some computation has happened so far and there is no carry until this point in time. Some computation has happened so far, but we don't know how many times we have kind of gone through this and how many times we have gone through this, all that we don't know. Okay, so, but we only look at 2 bits. Those 2 bits can come from something like 2 16-bit addition or 2 32-bit addition. So how many bits we have added so far before we look at the current input. So such information we won't be able to give through this picture. Okay, so that's what I told. You can remember some computation, not all. So let me write, remember some computation, but not everything that happens through this process. Okay, so now with this example you get to see that a machine like this has got finite states Now, how do we formally describe a finite state mission? And it has got something called states, then it has something called symbols, and when it reads symbols or when it reads a string, it moves from one place to another place, and it continues to stay at a particular state, or it can move from this state to this state, and in the process it can also output something. And so with this framework, let's formally define finite state missions, and then we will talk about its computing power, what languages that these missions can accept. Then we will talk about its limitations. Subsequently, we will get into its kind of how do we overcome these limitations, what variation we should bring into the model. Okay. So all that we will be describing shortly, and for that we will bring in formalism, abstraction, and we will describe the model by using set theoretic notation, and with that you can apply that in any CS application.